So what if I told you a single particle can be in two places at the same time, or even more places at the same time? I know, physics decided to glitch up, but it's real and it's called superpositioning. Okay, so let me break it down real quick and easy before your brains collapse like a wave function due to overthinking. So first of all, I am going to explain it to you how Schrodinger explained it. Okay, so Schrodinger is the guy who proposed the idea of superposition. Okay, so we have a box, a nice cardboard box, and we have a cat. Yeah. So we are going to put this cat in the cardboard box. Okay, and now we have a radioactive substance. We are going to put that in the box as well. Close the box. So now here's the catch. There's a 50% chance of the radioactive material to kill the cat, and a 50% chance of it doing absolutely nothing. Nothing at all. I know, boring, but it will not do anything 50% of the time. Okay, so let me now shake that up, and now let's see. And here is our cat. Okay, so is the cat dead or alive? It's dead. That's sad. May he rest in peace, our little soldier. But what if I told you, before I opened the box, before I peeked inside the box, there were hypothetically two cats. One cat was dead and the other was alive. So, in simple terms, superpositioning is oh, when before observing or measuring a particle or object, in our case a cat, it can be in all possible positions or in all possible states before we measure it. But what if I told you it's not really how it works? Okay, cats are way too big for this to happen. We need to go smaller, smaller, at the size of atoms or sizes smaller than atoms. Superposition occurs. Sizes of electrons, protons, neutrons, or whatever you can think of, gluons. Okay, at these sizes superpositioning occurs. So let me break it down even more clearly. Okay, so we have a cardboard wall, and we know there is a particle on the left side of the ball. We know it is on the left. Okay, so now let's travel back in time to when we did not know where the particle was. Whee! Okay, so we are back in time to a point where we did not know where the particle was. We only know that the particle could be either on the right or the left. Okay, so right now we have not observed it. We have not measured where the particle is. So there are kind of two particles. One is on the left, one is on the right. Okay, so once we observe it, we will find out the particle is on the left, and once we observe it, the wave function for the particle on the right will collapse. So basically a wave function is imagine it as a magical bubble. So this magical bubble holds all the possibilities, all the states of where an object or a particle can be, all the possibilities. Okay, and once it is measured, the magical bubble pops. Okay, and the wave function collapses. Okay, so once we observe it, the wave function collapses, and due to that, all the possibilities that were interfering on this system, on this plane, wouldn't be able to interfere anymore, and only one possibility would be able to interfere, and in our case that possibility would be that the particle is found on the left side of the wall. Okay, so this is also how quantum computers work. Okay, so as we know, computers have bits that could be either 1 or 0, that that are that are tools that the computer uses to complete tasks. So, but in a quantum computer, there are not bits, but rather qubits, qubits, however you want to pronounce it. Okay, so those are not 1 or 0, those are ones and zeros. So let me visually represent it to you on how a quantum computer works. Okay, so imagine this maze as a given task to a computer. Okay, so we have a bit. Okay, so this is a bit, silver color. Okay, so a normal computer, what it would do, it would randomly go down every any path at a random. Okay, any path, it will go here, here, anywhere. Okay, and after a while it will find the path, and until it is completed every path in the maze, it will, and then it will say it's the which is the shortest path. Okay, so but if this was a quantum computer, okay, so there would be qubits. Okay, so we would, in a qubit, we will start off with a one agent, and as it moves forwards, if it sees a diversion in a path. Okay, so like here, it is going here. Okay, for example, right now, and it has these two paths. Okay, so it would split. Okay, one would continue down a path while the other is there, uh, and when it finds another diversion, it will split again into a qubit, and while every and like those, it will split at every possible time it finds a diversion in the path. Okay, till it till it completes the maze, and that so this splitting into the multiple will occur at every diversion until it finds the exit. Okay, so once it's found the exit, the other agents would collapse. Okay, will and we will end up with the final one, which is at the exit. Okay, so so uh, we know that it's in superposition, and only one agent is real. Rest are just split up. This is how a quantum computer works. So you might be wondering, what is this helpful for? So no, even though normal computer is very fast, but doing stuff like finding a specific face in a crowd of thousands, hundreds of thousands, whatever, a quantum computer would be a lot faster than a normal computer, as it would have qubits that would split into multiple. For example, in this maze, it was split into multiple agents till it finds the correct one. So in my example is finding a face in multiple amounts of faces. uh, uh, as the qubit sees another person, it will split, and it will split into multiple agents till it finds that one face, specific face is what it's looking for. Okay, so that's how a quantum computer is faster. So I hope you enjoyed my video. If you didn't, leave a hate/feedback comment in the comment section below, and I will catch you in the next one.